purpose of this video is to explain how a uranium and thorium based nuclear reactor work. To begin, let's ask a few questions. What happens inside a nuclear reactor? What happens inside to create the energy we use? What processes occur inside? And how does this process begin? All nuclear reactors are based on a process called nuclear fission. Nuclear fission occurs when a nucleus, as seen on the left, absorbs a neutron, which is seen on the right. This creates a bigger nucleus. However, this larger nucleus is very unstable. This unstable nucleus splits up into two smaller nuclei. In addition, one or two neutrons and an extreme amount of energy in the form of heat are left over as well. This heat is harnessed and is converted into electrical energy using a turbine and a generator. We will now discuss how nuclear fission is utilized in a standard uranium reactor. Like most reactors, uranium reactors require two kinds of fuel to create electricity, a fertile fuel and a fissile fuel. A fertile fuel is an isotope that cannot undergo nuclear fission. It needs to absorb a neutron in order to break down. This new isotope is called the fissile fuel. For a uranium reactor, the fertile fuel is uranium-238 as indicated by the yellow circle. This isotope gains a neutron, then proceeds to eject some neutrons while converting some of its own neutrons into protons. This process occurs twice in the uranium fuel cycle. This leads to the creation of fissile plutonium-239 as seen in red. Once this occurs, the fissile fuel releases an extreme amount of heat as it breaks down. This takes place in the core of the reactor. Above depicts the basic components of a standard uranium reactor. We begin at the reactor where nuclear fission occurs. The heat from the reactor is then used to convert water into steam. This takes place inside the boiler. This steam then moves to a turbine, which causes it to turn. This mechanical energy caused by the spinning of the turbine is converted into electrical energy through a generator. Usually, most of today's nuclear reactors are located near a large mass of water. This serves to cool the steam after passing through the turbine. As steam meets with a cold reservoir, it condensates back into water and is then pumped back to the boiler for reuse. A liquid fluoride thorium reactor functions similarly to a uranium reactor in the sense that both utilize nuclear fission, but a lifter uses thorium as the fertile fuel instead of uranium. Like uranium reactors, there's both a fertile fuel and a fissile fuel within a lifter. In a lifter, thorium-232 serves as the fertile fuel. This is a natural occurring isotope. Once it absorbs a neutron, it becomes unstable and releases two neutrons and gains two protons. What is left is fissile uranium-233. The heat from the breakdown of uranium-233 will create the electricity in a generator, like in a uranium plant. This is a basic model of a lifter. Like a uranium reactor, the fissile fuel is located in the core. However, instead of water carrying the heat from the reactor to the turbine, a lifter uses a molten salt. Molten salts are salts that convert into a liquid when exposed at high temperatures. These salts have many properties that are well suited for lifters. Some include that they have a high heat capacity, they operate at near atmospheric pressure, and are excellent coolants. These molten salts carry the heat from the reactor core to the heat exchanger. Once there, a second molten salt comes and absorbs the heat, and is then carried to a gas turbine. The salts are recycled to their original locations to retain as much heat as possible. The gas turbine works in a similar sense to a steam turbine, except for the fact that the gas in the turbine is ignited to create electricity.